Hello, my name is William Weisner. I'm a mechatronics engineering major here at KSU, and I'm the mechanical lead on the AUV team.
Hello, my name is Paul Piper. I am a senior this year at Kennesaw State University. I am a computer engineering major, and I am the software lead for Kennesaw State University's AUV team.
Hello, my name is Dante Orlando, and I'm the electrical lead for the KSU AUV team. I am a junior at KSU in electrical engineering.
Charybdis hull design can be divided into two main subcomponents: the outer frame, which provides overall structure and stability, and the inner frame, comprising the structures that hold the housing tube, battery tubes, and computer components. Our overall hull design has a simple but effective organizational system that allows easy maintenance and quick disassembly. In accordance with our competition goals this year, the mechanical team introduced several improvements to the hull. In order to perform complex spinning maneuver as we enter the start gate, we had to address issues with the stub's stability. The outer frame was lengthened to allow better weight distribution and to decrease instability from the heavy batteries. We also added a locking ring to our housing tube to provide better structural integrity to the cantilevered housing frame. The mechanical team also supported the torpedo launching system by integrating a universal mounting system to the outer hull. This design choice was pivotal because it enabled us to interchange various subsystems. During the development phase, we utilized a multi-tiered approach for changes to the hull. After identifying our project goals, team members met for brainstorming sessions where we solidified designs and collaborated on system integration. While working on sub stability, we used static simulations to determine proper structural parameters such as the additional length needed on the frame to counterbalance the weight of the batteries. Both the mechanical and electrical teams had to collaborate extensively during the optimization of the inner frame to ensure the structure provides sufficient room for components. After making CAD designs, we also implemented parallel prototyping with multiple one-to-one scale models for design efficacy. Additionally, we conducted final evaluation through weighted decision matrices to test if the final designs accomplished our task goals effectively.
Charybdis utilizes two Logitech C920 HD web cameras for our visual detection. Utilizing them in both a forward-facing and downward-facing orientation, we take snapshots using a single-shot detector method and pass off the images via OpenCV for post-processing. This allows us to clean up the images and helps the neural network make more accurate predictions. We decided to go with a multifaceted approach to optimizing our submarine's vision. By using a combination of white balancing, color correction, contrast stretching, histogram stretching, and equalization, we were able to clean up the images that the sub takes in order to improve visual recognition by a fair margin. Additionally, using edge detection helps to identify targets, determine distance, and make more accurate assessments. The enhanced images and videos are characterized by reduced noise level, better exposedness of dark regions, improved global contrast, while the finest details and edges are enhanced significantly. This overall lends itself to our faster RCNN model, leveraging the TensorFlow Object Detection API. Due to COVID restrictions throughout most of the year, finding time to test the sub in the water was few and far between. Thus, we decided to use simulations as much as possible to help us test new state machine movement algorithms, such as spinning while maintaining forward movement. We leveraged the ArduPilot SITL, or Software in the Loop simulator, which allowed us and our software team to run simulations independent of hardware. In addition to using simulations, we made extensive use of software such as Jupyter Notebook in order to test new filter settings in OpenCV while passing images through. Jupyter Notebook allows us to rapidly test new code or algorithms by providing immediate output, isolating code segments, and being in a highly shareable format. This improved our deployment times and reduced downtime between software iterations on our state machine, OpenCV, and neural network code.
The hydrophone system was designed as a means of capturing and filtering out the varying frequencies that can be found in competition. The way that the hydrophones are set up to complete this function is through the use of IC filters made in parallel along with multiple capacitors. The amplifier circuit amplifies the signal picked up through the hydrophones and the IC filters themselves. The competition strategy for the hydrophones was to allow the sub to pick up the frequencies that were being emitted through pingers. These pinger frequencies that are being produced could range from 25 kHz up to 50 kHz, and how the sub would know what frequencies to look for and focus on was through the IC filtration system that the team developed. This system was made up of IC filters that had different filter modes for pinpointing what frequencies to allow through and what frequencies to exclude. Those modes were a low pass, high pass, and band pass filter, and the ones that our hydrophone system needed was the band pass filter mode. This was simulated through putting together multiple ICs in parallel, coupled with the capacitors found on the amplifier circuit. The hydrophone setup was tested in a controlled environment at a pool using a pinger to emit frequencies such as 25 kHz for the hydrophones to pick up. How the signals were measured out to test if the hydrophones were capturing the signals being emitted was through an oscilloscope. The pinger was switched on about 25 inches away from the edge of the pool where the hydrophone setup was located, and the oscilloscope was able to read the 25 kHz signal being produced by the pinger from the hydrophone.